My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 464. In this lecture, I will continue my discussion on VC dimension. I request you to go through my previous lecture, that is lecture number 463. Just try to recall 4 points cannot be shorted by linear model, and hence VC dimension of a linear model is said to be 3. This is what a VC dimension is. It is the maximum number of points that can be shorted by a class of models for all possible configurations. Let's go to Wikipedia for VC dimension. Here you can see there are some examples of VC dimensions. If you go here, it says for straight line. Just see, for a straight line you will get a perceptron, linear model, etc. You can see it. You can see here, isn't it? There is a theorem called Radon's theorem, which says that 4 points cannot be shorted. This theorem comes from computational geometry. There is a whole area in computer science called computational geometry where you can prove theorems like this. This is the example that is given. One plane cannot separate two planes. Two planes, just say two planes can just see two planes. If you observe this one, just see here, two planes. You have two planes here, isn't it? Two planes can, but one plane cannot be shorter 4 points. That's why the VC dimension of this particular classifier is, what is this particular classifier's VC dimension? VC dimension of this particular classifier is 3, of a linear model is 3. Now you might wonder, some of these proofs are very mathematically intensive. From frankly speaking, I don't know some of these proofs. For example, you will see for boosting classifier, just see this one, for boosting classifiers like gradient boosting classifier. Just see, suppose we have base classes. What it says, just try to understand this particular, this one. Suppose we have a base class B of simple classifier whose VC dimension is D, isn't it? The VC dimension of the set of all such classifiers, there is a formula, T into D plus 1 into 3 log of T into D plus 1 plus 2. What is this T? T is base models, and each base model is of VC dimension capital T. It's related to statistical machine learning. There is also interesting bond which is very important. So VC dimension, VC, just try to refer this particular Wikipedia page on VC dimensions of boosting classifier. Just try to understand this formula. So VC dimension of RBF kernel SVM is infinity, which means this is very powerful idea. Remember, VC dimension is created by Wapnick, who also created support vector machines, kernelized SVM like RBF SVM. He shows in his work that RBF SVM is super powerful, isn't it? If VC dimension of one type of model is greater than VC dimensions of other class of models, let me say VC dimension of model 1 is greater than VC dimension, if VC dimension of M1 is greater than VC dimension of M2, then certainly model M1 is powerful. They are proven that VC dimension of RBF SVM equal to infinity, isn't it? It is extremely powerful model. So theoretically your RBF SVM is extremely powerful. This does not imply that RBF SVM is always best model in practice. Theoretically, RBF SVMs are super powerful as VC dimension of RBF SVM is equal to infinity. As we were discussing, if VC dimension of M1 is greater than VC dimension of M2, what does it mean? Certainly model M1 is powerful compared to model M2, isn't it? But theoretically, RBF SVMs are super powerful as we see dimension of RBF SVM equal to infinity. But in practice, lots and lots of application in practice, lots and lots of applications, you will see that RBF SVMs are not the best models, because theory is very cute and beautiful to prove. There are lots of assumptions that are taken to prove whole VC dimension theory. Some of them may not practically translated to real stuff. There is one more interesting use of VC dimensions in statistical learning theory. Again, there are lots of assumptions here. Assuming that your data is randomly sampled, your training and test data, your training and test data are sampled. There is a very interesting result in statistical machine learning which shows that the probability what your test error is based on train error. So you can say that your test error is always less than or equal to your train error with some probability. So what is the probability that your test error is less than or equal to train error plus some value? Here capital D is your VC dimension, N is the number of points that you have. So this is very powerful and interesting bond in theoretical or statistical learning theory. VC dimension and all of this beautiful theory is used by statistical learning theory. Let's assume your eta. What is this? Let me say like this. Let me say eta is equal to 0.01. Then what is my 1 minus eta? What is this particular value? 1 minus 0.01, which is nothing but 0.99. So you can say that your test error, less than or equal to training error plus some constant. What is this? This, let me say, this is some constant C. Some constant, we can compute this constant C. If you are using a linear model, you know that for linear model, what is your capital D? For capital D, for linear model, capital D equal 3. You could have capital N. Let me assume your capital N equal to 10,000 points, 10K. Let it be 10K points. Here your test in 10K points in your test data, and your eta equal to, let me say, 0.001. You can plug in all these values. You can simplify this. You will get the sum. You will get some value C. You will get some value C here, isn't it? If you plug, you will get some value. So now you can say that the probability of test error less than or equal to training test error less than or equal to training error plus some constant C. Let's assume we evaluate all of this. We got if you keep N value, D value, you will get some value C. Is equal to probability of test error plus training error plus C, some value C, is equal to, what is this, 1 minus eta, 0.99, which means with 99% probability my test error less than or equal to training error plus some constant C, and this constant C can be computed using your capital D, which is your VC dimension, and capital N, which is the number of points that you have, eta is that you have eta you have chosen 0.01. So you can come up with bonds like this. This is an interesting concept to learn. I hope the shortening concept will give you some idea of what VC dimension is. So it is an interesting, beautiful, elegant idea to learn. Just go through this. If you have any difficulty, please keep a comment. Thank you very much.